talk about regime switching, market evolution, and calibration.
Thank you. I mean, Bruno has already told how long we've been knowing each other. Should blame him for bringing me towards financial math, and I was really relaxed in my pure math at that point. Well, of course, I need a bit of money, and then he left Sogen, he called at Sogen, and then he called me and said, we need a math guy. Anyway, I was completely ignorant of markets, except it's turned on. Oh, that's when. Yeah, okay, right. Okay, good. Yeah, so I was completely ignorant of markets, except what Bruno told me about it. So Bruno was inundating me with all sorts of questions, and that's what is interesting, because there's something on his, you know, when I was young, I was in the big math, and Bruno was always very ludic, let's put it this way, always playing with little problems. Was doing at that time was already AI and different things. He was working also on how we perceive colors. He was always doing the. So when he went to those finance stuff, it was just one more game, one of those things that he was doing. And in my math, I had a hard time taking that seriously until I started doing it, and I found that by doing applied math, I increased enormously my knowledge of math. So it's like, I was focused on my dynamical systems, and then suddenly, I discovered all fields of math thanks to finance, thanks to other things also that but when you have to solve a real problem. So, okay, so let's go here. So thanks, Bruno, for changing my life. The regime switching, so it's really work in progress. I mean, I've spoken here. I haven't been as systematic as Bruno and Matthäus in coming here. There are some years where I didn't come. But you've seen several times my stuff on polymodels. The regime switching is something, a lot of people do that. If you think of it, you have, all those, basically the idea. No, why do I have to start with traditional multi-factor analysis? Okay, we'll see that. Yeah, okay, we'll speak of it. But basically, regime switching, we see that markets, evolve through different regimes. So that's why we saw stochastic volatility, etc. Volatility changes, correlations changes, and it switch from, sometimes they switch continuously, sometimes they switch brutally from one regime to another. And, but the difficulty, so it's very easy to simulate a regime switching model. You define regimes, you switch from one regime to another, and you simulate that. That's very easy. The difficult part in regime switching is to identify them once you get a time series. And that's something I've noticed, that I was surprised people doing statistics and probability. When you come from dynamical systems, we all know that given one trajectory, guessing the dynamics is practically impossible. So it comes as an a priori. I mean, this problem, which is an information theory problem, we know we don't have it. And statisticians absolutely believe hard that you can't find a solution, that you can't find convergence estimators and dynamicists. No, you can't. You can't. So you just try to grab some information somewhere to make some decision. So, okay. So, here, let's go fast. There was one of my slides on polymodels. Let's go to practitioner's question. That's also one of my slides on polymodel. What practical questions you are asking on markets to make decisions about risk. What are the source of risk? How far it can go? How frequently? Can I anticipate dangerous events? Can I diversify away? And you will see that those regime switching models, they give you some approach in the sense that instead of saying, okay, well, I have one model and I hedge against that model, and if something changes, I'm completely naked. No, you anticipate already in your mathematical model the possibility of other regimes. good example, which, we call that, cross-validation questions. When you try to get some model that will give you some prediction of some conditional prediction of a behavior of an investment conditionally to some risk factors that you have identified, then the question is, suppose you hedge according to those risk factors that you have identified, are you doing something that will improve your situation? Well, one way is to calibrate the model y hat on the past, look at the error, calibration error, and see whether the calibration error, the residual, but the out of sample error has bigger or smaller variance than your original signal. If your supposed hedge gives you an investment that is further away from your actual return from what you already had, then basically your hedge doesn't work. And then you will find out that a lot of multilinear factor models have this property of having what I call a negative prediction power. The consequence when you do portfolio optimization, well, by the way, Bruno has been a lot working on the sell side problem, pricing, identifying, etc. For the past, at the beginning I was working also on the sell side, and for the past 15 years I've been essentially working on the buy side. And that's interesting because today I see sell side and buy side converging back together with similar question with, for instance, what Sebastian was talking about, etc. So what you have, when you try to optimize and you don't account for regime switches, what happens is that you try to optimize some portfolio like this, expected return divided by risk, but your risk is something that is measured according to your model. And what happens is that when you optimize, instead of increasing the green, in fact, essentially you reduce the red. And the consequence by reducing the red, in fact, what you maximize is not your Sharpe ratio, is a ratio between hidden risk and measured risk. So basically, you increase your proportion of hidden risk. And that's the basic consequence if you don't do your optimization correctly. The diversification. Now we go to multi-regimes. Suppose that your probability distribution is a Gaussian mixture, for instance. Just take it like this. Every P1, your real probability is a mixture of probability P1 to PQ with, so each of them here is something like Gaussian, but with different covariance matrices, some with, representing regimes with high volatility, and the probabilities of being in such or such regime are like this, with P1 bigger than PQ, etc. If you do a naive optimization, what will happen is that you will optimize according to something that's close to P1 because that's the biggest probability. That's the one you will observe essentially. And so you will diversify your way. You will enter into some portfolio that if the market stays into the major regime, the blue sky regime, then you are well diversified. But by being well diversified in this regime, if you go to the other regimes, you are not. So what does that mean? That basically you reduce your volatility if the market is in that situation. So your standard deviation shrinks, but not in the other regimes. So in fact, you increase massively your fat tails. The ratio between the most probable volatility and the extreme volatility, let's say the extreme volatility was twice as big as so your sigma 1 was and your sigma 2 was twice sigma 1. And now you have adopted a strategy that reduces sigma 1 because you have optimized your portfolio. And so the ratio between sigma 2 and sigma 1 has increased. So that's what we're going to address. So how do you do a hidden Markov model? A hidden Markov model is something where you model different certain types of regimes here. Each regime, I made it very simple, like some Gaussian distribution, but in n dimensions. So the idea is that you have a market, and then you map the market onto some abstract mathematical world where things are Gaussian. So if you imagine stocks, you just take the log of the stocks and things like this. And then if you're in discrete time, you have a probability matrix, what we call a stochastic matrix. The sum of the rows of the matrix are always equal to 1. And this is a Markov chain of switching from one regime to another. In continuous time, you can also have that with a semi-group generator, and then you get some exponential transition between regimes. So the idea is that you see, where is it? Yeah, here it is. So the idea is that you have, for each regime, a usual Gaussian distribution, but underneath you have the dynamics between the regimes. So the question is, so you can simulate that, with there is a theorem which is not very difficult, where you can show that because the sum of rows equal to 1, that means that the transpose of that matrix applied to the vector 1, 1, 1, 1 is also 1, 1, 1, 1. So 1 is an eigenvalue of that matrix. Because it's an eigenvalue of the transpose of the transition matrix, it's also an eigenvalue of the matrix itself. That means that there is one distribution of probability which is invariant. In other words, there is a certain distribution of probability of regimes where it will transit to the same distribution. And in fact, you can show that if you start from anything, and provided the transition probability are non-zero, if you start from any probability and you run the probability matrix, it will eventually converge towards that distribution which we call ergodic. So that's this distribution pi here, which is invariant under the probability, the transition probability. If you run the multi-regime for the very long run, in fact, you will compose plenty of steps which asymptotically become ergodic, and you lose the mixture, essentially central limit, and you converge to one single regime, which is the average of those. If you want to be Ricci neutral, you can assume that mu infinity is 0, which doesn't mean that every single mu k is 0. That's quite important. So the question is, how do you calibrate those regimes? And that's where it becomes difficult. The question, you have two things to do. Identify the regimes and calibrate the transition probability. Identify regimes, how do I do that? Basically, you go through different periods, different windows, and you look at, for each window, covariance matrix and drift. That defines a Gaussian distribution within your market. Those Gaussian distributions, you can, then you get, a certain, you would like to say, well, that path within the set of all possible Gaussian distribution goes through some areas. It goes there, stay there for some while, then jumps, then goes there for some time, then jumps, then go there for some time, etc. That would be nice, except that there is a difficulty. We all know that if we take a stochastic process in dimension 1, it goes back. If in dimension 2, it tends to come back as well. In dimension 3, it does not. In here, we're in dimension several hundreds. It never comes back. So wherever it goes through somewhere in the space, it does not come back. So how do we deal with that? There are two things that we have to do. Again, I'm talking, it's work in progress. I've done lots of tests, etc. It starts giving some results. So three things we do. First, we reduce the dimension. Instead of looking at markets with hundreds of stocks, etc., we just identify the markets with a few indices. Typically, we take 10 to 20 indices, not two. I mean, there are a lot of people, they simply look at the common practice. It's just like, okay, well, when we have only high volatility and low volatility regimes, and that's all. No, it's not sufficient. The markets are much more complex, and I will tell you why. So you reduce, but still, if n is 10, you see that we're above, we're in close to 100. I mean, several tens. If n is 20, you're above 100. That's complicated. So we use, those pictures. You've seen those pictures where you have a set of distances between numbers which are in high dimensions, and you project them onto a plane where you try to fit the kind of distances. And so that's the second time. This one is pretty efficient to tell you, that we're in this area or this area, etc. It's like defining big cells in high dimensions where you say, I'm in that direction, I'm in that direction. In other words, you try to find in very high dimensions what are these finite dimensional submanifolds in which I'm not far away from lying. And then, so that's the second thing. So now the projection does have some recurrence. You have areas, and you do have. So last thing that I have not done yet, but with us, the next thing that we're working, is identify breakpoints so that you can say, okay, well, instead of taking, time windows that are regularly spaced, I identify breakpoints and say, okay, let me see between breakpoints what the statistics look like. Then I have a breakpoint and I have new statistics. Then I have a breakpoint, I have new statistics, etc. And that would probably improve the signal-noise ratio to get that. The second thing is transition probabilities. The very classical algorithm, which is just counting, is Baum-Welch. It's too imprecise. We've used some support vector machine, actually, that gives more correct results. Crisis prediction. So that's come here. That in here, we are putting the finger on what is very difficult to calibrate. Basically, okay, imagine a traffic light where you have green, orange, red. Now you look at the regime of flow of cars. Light is green, cars go. Light is yellow, cars go also. Yeah, light is red, cars stop. Now, what happens? What's the probability transition from green to red? 0. It has to go through the yellow. So what's the probability transition from yellow to red? Very high. But so green and yellow are basically very hard to distinguish from the statistical behavior, but their transition probability are completely different. So now we can simulate a situation like this where we have two different regimes that statistically are very much alike, except that one switches with high probability to a crisis regime, whereas the other one is very stable. Can only switch to one of those regimes. So these are those intermediary regimes. So you see that this kind of thing, you cannot see it from the statistics. So in other words, it's the same question as what does the market look like before the crisis? What does the weather look like before the storm? Is there a certain kind of calm before the storm that's different from the calm that stays calm? Like those guys, they have, there's sailors who smell that this calm is something, that may switch to a storm. That's what we want to identify. So we can simulate it. Now, given the actual behavior of markets, identifying them is not so easy. So people will tell you, yeah, there is a higher correlation. If you see a bubble, you see big drift for some time. We've done lots of tests like this. Yes, we see things, but it's not obvious. That's one of the major difficulties of those regime switching models. That gives you, typically, I was saying, this typical 2D projection of high dimensional. So here, every dot represents a covariance matrix made over a 6-month period on the global markets. The colors represent the clustering. And actually, these correspond, I think this one corresponds to some calm situation. This one corresponds to crisis. So the yellow, are those kind of transition regimes. So that was kind of, this was interesting. That shows you here the regime as we see them on the history of the S&P. You see, that well, you have like, we showed it on the S&P to understand the real behavior of regime. Yeah, sorry, the yellow was the crisis stuff, and the orange and the yellow was the crisis stuff, you see. And you get those pink here, but you have to see them in conjunction with other indices. I just, showed you what it looks like. Now, once we have that, portfolio optimization, basically the idea is simple because we say, okay, well, let me simulate those trajectories. Simulation is easy. And let's see, how I can optimize. I have both the drift and the volatility. So we have everything we need for simulation. And we can compare that to forcing only one regime, which would mean exactly a Markowitz optimization. And you see here, so this was made over a 10 years period, going through the crisis, using the multi-regime versus not using regimes, so that the green one is Markowitz and the black one is a multi-regime. Essentially, you see that it strongly differs in the behavior during the crisis. Then in the recent period where they had a big rally of the market, the single regime, that was 7th industrial sector, that was with Eric Dagobert, who was my co-worker on this question. He said, he's running currently all the sectors. He took half of the sectors because it was too long in terms of calculation. So you see we're a bit flat here. Nothing is perfect. That's, we get all the sectors, now 11 industrial sectors, but we just see, the first start until 2010. Should see, in a few days, the full simulation. The other thing, so what's the relation with polymodels? Polymodels is this principle where I analyze one given asset with respect to a lot of different factors, but each factor independently. So it's like, I get, instead of saying, okay, this is, you have the conditional expectation with respect to x1, then I forget x1, the conditional expectation with respect to x2, etc. And I look at this collection of models as my base tool. Now, if unlike the multi-regime, where if I give you the regime, I can simulate it. If I give you all the functions fi, it's very difficult to find. Yeah, you can use EM, etc., but it's quite difficult to provide some simulation that has those conditional expectations. But it reads pretty well the risk, and here is a regime that, okay, so multi-factor, the relation between the relation between polymodel and hidden factor model. Suppose you have a hidden factor model, and then you want to see why the polymodel will give you a nonlinear shape. That's because suppose that now I'm telling you, okay, well, I have this asset, this fund, this stock, and I want to simulate the impact of a 1% move of the S&P. Well, 1% move of the S&P, I do some Bayesian calculation of the probability of the regime with low volatility. That's the most probable one. So you get the beta with respect to that regime. But if I'm telling you, okay, 5% move of the S&P or 10% move of the S&P, then the regime with low volatility becomes extremely improbable. And the most probable regime will be a regime with higher volatility, therefore a different beta. And that's what you see, here. You will see, that if this is, yes, my risk factor, is this my expected stock return, then you will see, you know, on the extreme, it's like you get the beta corresponding to some extreme regime. Right in the middle, you get the beta corresponding to some medium regime. So the existence of those regimes implies this nonlinear response. And that's, you know, the deep relation. As a consequence, again, if you know that you have more nonlinearity, if those probabilities react more, when do they react more? When precisely the probability of switching from low volatility to high volatility is bigger. So if you are in a regime that is more likely to switch towards a crisis, those pre-crisis period, calm before the storm, they will tend to display more nonlinearity. And that's one of my students, Yao, is working on precisely measuring how nonlinear are the polymodels and take that as a measure of something that could be a crisis indicator. So she has this, like basically she's plotting here the square of the Sobolev norm, of the H2 Sobolev norm of the polymodel, and against not the S&P but an average of stocks which is biased. But anyway, I mean that shows, you know, something where you see basically this big surge just before the crisis. Yeah. Well, I think I'm practically done because. So, well, I have a couple of pictures. I want to make a comment here. It was tough for me to find pictures with Bruno had two properties. You know, I could show them in a math conference and not destroy his wonderful family life. And also, you know, I noticed that, you know, even if I wanted to blackmail him, because I have a number of pictures that are there, I would have a hard time because they are completely buried somewhere in Paris. So I had to find pictures from the digital era. So they are more recent. So that was just a few days ago. That was so. The left one, which is quite interesting, was just the day before the one that Matthias was showing. That actually is my birthday present to him, that beautiful yellow shirt, which just to remind him that, you know, when he was young, he was having those beautiful shirts, and I would like to see him a bit more often like this. And we were talking of the kids. So Leo, when he was not that tall, very successful at opening a bottle of champagne. And that's Bruno with my daughter, Laina, and friends of hers. I was in some Brazilian music bar in Soho, if I remember, in 2012. Bruno, thank you.